So our next talk is on testability and goodness of fit in missing data models, and it's Razieh Nabi who is presenting in person.
Hi, everyone. First off, I'd like to thank our program chairs and the members of the organizing committee for putting together this excellent conference. It's a pleasure to be here. So my talk is on missing data, and it's a joint work with my colleague, Rohit Bhattacharya from Williams College. The thing about working in missing data is that you don't have to spend much time motivating it, because we see missing data everywhere for a variety of reasons. There could be issues with data collection, dropout, censoring, and so on and so forth. And the causal inference and missing data have been, they share a lot of similarities, and they are analogous in terminology, theory of identification, and statistical inference. So oftentimes in causal inference, we form our problem as a missing data problem because responses to some interventional distribution, some interventions are not observed. And also missing data has been phrased as a causal inference problem, where we think of missingness indicators as treatment variables that can be intervened on. So we think of variables as counterfactuals had there not been missingness. So similar to use of graphical models in causal inference, we sometimes like to represent missing data models graphically as well. But the question we are focusing here is whether the encoded assumptions in a missing data graph are testable or not. And if they are, how do we design empirical tests for those? So let me introduce some notation. Let's say we have vector X that denote vector of k random variables with finite support and joint distribution Px. Given a finite sample from Px, we see variables have missing instances. So we let this vector R to denote the binary missingness indicators. So for variable xk, if it's missing, then rk is 1, and if it's not, then rk is 0. And what we observe is just a coarsened version of x, and denoting by x star. So x star is deterministically defined with respect to x and r. So x star of k is just xk when rk is 1, and it's just question mark when rk is 0. So there is a causal interpretation of this tuple xk, rk, x star of k when we think of missingness indicator rk as a treatment variable that can be intervened on. So therefore, the corresponding variable xk can be thought of as a counterfactual, as a variable had we intervened on and set the missingness indicator rk to 1. And x star of k is just a factual variable that we observe. So sometimes to emphasize this causal connotation, we use a superscript x1 to denote the counterfactuals, but I'm just sticking with this notation for simplicity. But I do refer to x as the counterfactual vector, and I do refer to x star as the factual or as the proxy variables. We also could have variables that are always observed, but for simplicity here, I'm assuming that all variables have missing values, but incorporating variables that are completely observed is no big deal. So a missing data model is a set of distributions defined over these variables, counterfactuals, missingness indicators, and proxy variables. And by chain rule of probability, I can just write down this joint distribution as a product of marginal distribution over counterfactuals X, calling it the target law, and then the conditional distribution of the missingness indicators given this counterfactuals, calling this the missingness mechanism. And then there are the leftover terms that correspond to these deterministic relations. So this the density of the proxy variables given the counterfactuals and missingness indicators. And the product of the target law and the missingness indicator together, missingness mechanism together, I'm referring to as the full law. So the deterministic relations between proxy variables, counterfactuals, and missingness indicators are similar to the consistency assumption in causal inference. And the observed data law is just the marginalization of the full law when we marginalize out the counterfactuals. So that would be just the distribution over R and proxy X star. So a missing data workflow, a typical workflow looks like this. We define the estimate we are interested in. It's often done in the absence of missing data, and that's usually a function of either the target law or the full law. But then we assume a model that links these counterfactuals, missingness indicators, and proxy variables together, usually by imposing independence restrictions between these variables. And oftentimes we like to encode these set of assumptions using directed acyclic graphs. But then in the assumed model, we think about identification and estimation, and maybe conduct sensitivity analysis to reflect on the assumptions. But the validity of any identification and estimation result would rely on these independence assumptions encoded on the missing data graph or the missing data model to hold true. But in order to test these independence assumptions, we have to think about their implications on the observed data distribution so that we can design empirical tests to using finite samples, but samples that are only partially observed. And sometimes, unfortunately, we may not be able to test these encoded assumptions. And it's similar to, for example, saying that conditional ignorability in causal inference is untestable, but sometimes we can test these assumptions. And this is the focus of this paper, to expand on testable implications in missing data graphs that resemble ordinary conditional independence restrictions in the full law, but they translate or they manifest as generalized independence restrictions, also known as Verma constraints, on the observed data distribution. And then design empirical tests to evaluate this in 3 broad classes of missing data DAGs using weighted likelihood ratio tests and the odds ratio parameterization. Let me quickly introduce what the missing data DAG is. So we define the missing data model with restrictions on the full law that can be represented using graphs similar to causal inference. But there are 2 major distinctions between missing data DAGs and regular DAGs. The first distinction is that we put observed and counterfactual variables on the graph at the same time, but there are also certain edge restrictions. The first set of edge restrictions is related to the deterministic edges, because we said that proxy variables are deterministic functions of the missingness indicators and the counterfactuals. So then no counterfactual or missingness indicators can point to proxy variables of other variables. They can just point to its own proxy variables. And the second set of edge restrictions is something that we can think of as like no interference assumption, where we say that missingness indicators cannot point to counterfactuals. I call it the no interference assumption because what it's saying is that each variable is actually only relies on its own missingness indicator or its own treatment, not the treatment of other variables. But this assumption can be relaxed, but for this talk, I'm assuming this set of edge restrictions. But in the original or in the traditional missing data DAGs that was introduced by Mohan and company in 2013, there was also this implicit assumption that there are no edges from proxy variables to missingness indicators, but this assumption can be relaxed, and we do allow for those kind of edges. So, and then the statistical model of a missing data DAG would be just the joint distribution that can be factorized as a product of conditional density of each variable given parents on the graph. And familiar concepts like deseparation and factorization and Markov properties, they all carry over. These are examples of some missing data DAGs. On the top left corner is an example of missing completely at random because the missingness indicators don't have any either observed or counterfactual parents. And the other 2 examples in the left column are examples of missing at random or MAR models where the causes of missingness are all observed. And all the 3 models on the right column are examples of missing not at random or MNAR models, where at least the missingness of one, the causes of the missingness indicator for at least one variable is a counterfactual variable, is something that is not fully observed. So the top one is an example of the permutation model that was introduced by Jamie Robbins in 1997. And this is what I'm mostly focused on in this talk. So as you can see, there are by these Markov properties, all of these graphs represent different set of independence restrictions. And these independence restrictions correspond to the absence of edges between variables. But the question is, can we test these independence restrictions? So the thing is, as I mentioned, sometimes we cannot test these independence restrictions. And if the assumptions in a missing data model or in a missing data DAG are provably untestable, meaning that they don't really impose any restrictions on the observed data distribution, then the full law that is Markov relative to this missing data DAGs is said to be non-parametric saturated. And the permutation model that I briefly mentioned in the previous slide is an example of a non-parametric saturated model. And when it was introduced by Jamie, there wasn't he didn't provide a DAG representation, but there does exist a DAG representation of this model by allowing for the proxy edges to point to missingness indicators. And another example of a non-parametric saturated model is what's known as the no self-censoring model, but that doesn't have a DAG representation. It has a chain graph representation, which includes directed and undirected edges. But submodels of these non-parametric saturated models can be tested, and that's what I want to talk about. So let's look at the permutation model a little bit more closely. So given an ordering on variables X, so the permutation model encodes this set of restrictions that each missingness indicator is independent of its corresponding counterfactual and the counterfactuals that come before it, and given the prior observed information and all the counterfactuals that come after it. And as I said, the permutation model is non-parametric saturated. And the way to show this, if you're familiar with the semi-parametric theory, is to just think about driving the tangent space of the observed data distribution and realizing that this doesn't actually restrict any, that doesn't pose any restrictions on, it includes all the observed data distributions. So here's an example of an MDAG with 2 variables for the permutation model. And there are restrictions with respect to the missingness indicator R1 and missingness indicator R2, but these 2 assumptions cannot be tested using observed data distributions. But submodels of this can be tested, and we consider 2 submodels. One is the sequential MAR model, and the other one is the sequential MNAR model. I'm going to focus mostly on the sequential MAR to give you the general idea. So here's what the sequential MAR model looks like. As the name suggests, it's a MAR model. So the missingness indicators would only have causes that are observed. So each missingness indicator is independent of all counterfactuals given prior observed information. At the bottom is the example of the sequential MAR model with 3 variables. So without the dashed red edges. If you ignore the red edges, then this model is just a MAR model. And comparing this with the permutation model, when we do include these red edges, so the sequential MAR model is going to assume extra independence restrictions, and that's just listed in the middle of the slide. And we can do test these restrictions, but the thing is, relying on the information in prior literature, we wouldn't be able to test these restrictions. And here's why. So switching back to the model with only 2 variables because it's simpler. So what we want to do, we want to test the absence of the edge from X2 to R1. So we want to know whether R1 is independent of X2 or not. So the criterion that was proposed was by Mohan and Pearl in 2014, and they said that the separation condition that is displayed on an MDAG can be tested if the missingness indicator of the counterfactuals that are involved in the deseparation statements are already conditioned on in the separation set, or can be conditioned on without really spoiling the separation statement. So here, we want to test whether R1 is independent of X2, but X2 is a counterfactual, but the corresponding missingness indicator R2 is not in the conditioning set, but we cannot also include that in the conditioning set because conditioning on R2 would open up a collider at R2, and that would mess up the independence restriction that we want to test under the null hypothesis. So then one might conclude that this independence is not testable, but it is. So momentarily, let's assume that everything is binary. So X consists of binary variables. What we want to do, we want to compare the number of parameters in the full law and compare it with the number of parameters in the saturated observed data law. And if the full law has fewer parameters, then that does mean that the full law is restricting the observed data law in one way or another. So here, looking at the parameterization in the full law, so that's the number of parameters we are looking at in P of R and X, that would be 7 parameters. But if you look at the number of parameters in the saturated observed data law, that would mean we would have to specify 8 parameters. And that's just like we can count this using what's known as the pattern mixture factorization, which simply looks at the joint distribution of R and X star and writing it down as P of R times P of X star given R. So 7 is less than 8. So what it means is that the full law is restricting the observed data law, at least in the discrete case. So this contradicts our earlier conclusions, but these contradictions are expected because the criterion that I mentioned in the previous slide is a sufficient criteria. It's not necessary. So, but what I want to show you next is how to actually test this independence restriction. So the issue here for testing the independence between R1 and X2 was that if we do condition on R2, that opens up the collider at R2. But what if there wasn't any edges pointing to R2? What if there wasn't any collider at R2? So from a causal perspective, removing edges correspond to doing interventions. So what if we intervene on R2? So an intervention on R2, so graphically speaking, it means that we are removing all the edges into R2. And because it's a missing data problem, we are interested in intervening on R2 and setting it to 1, because otherwise it's not a well-defined intervention. So setting R2 equals to 1, then the proxy variable would be the same as the counterfactual variable. So we get rid of the independence, and we get rid of the deterministic edges. So what we end up at is the conditional DAG in C. So probabilistically speaking, what does an intervention on R2 means? So it means we are taking the full law and divided by, so to speak, the propensity score of R2. And that's just the conditional distribution of R2 given its parents. So that's what it means to intervene on a treatment in causal inference. We are just dropping the propensity score of the treatment from the factorization. So at the bottom one is the intervention distribution that we obtain by this truncated factorization of the full law, dividing it by the propensity score of R2, which is the P of R2 given its parents. So in this intervention distribution, X2 is observed. So we can test the independence between R1 and X2. That's what where the Verma constraints comes from, is just the ordinary conditional independence on the full law now translates into this generalized independence restrictions, or this independence restriction in the interventional distribution. But how do we empirically test this? So we want to know R1 is it independent of X2 or not? So what we can do is to compare goodness of fits between P of R1 and P of R1 given X2. P of R1 is simply the proportion of complete cases for X1, but how do we fit parameters for P of R1 given X2? And so assuming that there exists an estimating equation with respect to the full law to estimate the parameters, then we just need to reweigh this estimating equation and just only focus on observed rows for X2 to fit the parameters, and then we can compare the goodness of fit. So this is how, this means, using prior knowledge, we wouldn't be able to test the independence between R1 and X2, but there does exist a testable implication on the observed data law, and we can test it using this weighted likelihood ratio tests. So generalizing this to cases with more than 2 variables have some subtle points that I just want to emphasize here. And okay, here we want to do the independence test involving the missingness indicator R1 and R2. So for example, for R1, we want to know whether R1 is independent of X2 and X3 or not. But we cannot condition on R2 and R3 because they open up the colliders, but we can do this test using the intervention distribution where we do intervene on R2 and R3. And that would require using this weighted estimating equation to fit the parameters. But the weights we are using in this weighted estimating equations involve as estimating the parameters for the propensity score of R2 and the propensity score of R3. The propensity score of R3 is easy to fit because the causes are all observed, but it's a little more subtle for fitting the propensity score of R2 because there are some counterfactuals in the conditioning set. But in order to estimate the propensity score of R2, we need an intermediate step where we only intervene on R3. So that would require another weighted estimation for estimating equation for estimating the parameters of the propensity score of R2. So we generalize this to K more than 3 variables. The algorithms and the general theory exist in the paper. But what I want to say is that as we proceed with the test, so one quick or one intuition for this to be able to use data as efficiently as possible in each step is to start from the last step, test independence restrictions with the missingness indicator RK-1, moving on to RK-2, all the way to R1. But what the thing is, as we proceed with the test, we are restricting ourselves to fewer and fewer samples that can impact the power of our test. But it could also be this procedure, the weighting estimating equation could be susceptible to model misspecification. So it would be as future directions to think about more flexible methods to use data so that we can use data more efficiently. And the sequential MR model is actually just testing now the edges from proxy to missingness indicators that I'm going to skip. And the other non-parametric saturated model that I mentioned was the no self-censoring model, where we assume that each missingness indicator, is independent of a counterfactual given the rest of the graph. And we can do test submodels of this, but it's using the odds ratio test. And just wanted to make a quick point that choosing the supermodel is important. Like the graph in A could be a submodel of the permutation model in B. It could be also a submodel of the no self-censoring model in C. It could also be a submodel of the graph in D, but the graph in D is actually not identified, and that is the only graph with 2 variables that we know of where the target law is actually not identified, and we do provide counterexamples for this. We can incorporate unmeasured confounders also on the graph, and coming up with a data-driven structural learning approach and more flexible semi-parametric approaches or future directions. Thank you.
We have the discussion now, so is it on the same slide for discussion?
It's not on my slide.
Maybe you should. Okay, perfect. So Kartik Mohan is our discussion, and I believe he's also virtual. Oh, it's she, sorry, it's and she is virtual, pardon.
Hi, good morning from Oregon. So can I share my screen, or how does this work?
I think the best is if you tell me I click, if that's okay, because of the time constraint.
Yeah, okay.
Thank you.
Okay. So good morning from Oregon. It's a delight to engage in a discussion about the paper authored by Razieh, Nabi, and Rohit and Bhattacharya. Like most research endeavors, this work builds upon and enhances existing research in the field. Regarding the handling of missing data and testability early, can you please move to the next slide, please? Regarding the handling of missing data and testability, early work by Roderick Little in 1988 laid the foundation by deriving tests for the missing completely at random category. However, since then, advancements have been made to encompass all categories of missingness, including missing at random and missing not at random. Specifically, my own work with Julia Pearl further extended these developments by introducing tests based on graphical models, specifically addressing conditional independent statements in the missingness graph. The current paper takes our work one step further by leveraging Verma constraints. This extension allows for more robust and comprehensive treatment of missing data, pushing the boundaries of what was previously achieved. Also, this paper leverages a different kind of representation wherein they allow edges from the proxy variables, X star, to the R variables, which was something that we didn't do previously, and that was sort of very interesting. Undoubtedly, this paper is a must read, as it offers several surprising and interesting results. In particular, theorem 4 is my personal favorite for its significance and implications. So the insights provided by work have the potential to advance the field substantially. Thank you very much.
We have time for one short question if someone has one. Yes.
Just, a very nice talk. A very nice talk. Just one quick question. In the case where you don't derive any constraints, is it still possible that there are inequality constraints that could be tested?
There could be inequality constraints. Yeah, potentially, but we're just like focusing on equality constraints here. Yeah.
Thank you.